Hi folks, today I will be talking about something that relates to both biology and physics, squids. So this is the Pacific flying squid, and as the name implies, it can fly. I happened to come across this species of squid when I watched this video from TED on YouTube. Anyways, I have never known that squids could fly, and this knowledge instantly made me love these adorable cephalopods even more. Essentially, in this video, the presenter talked about what exactly these squids do. These squids are able to glide near the surface of the ocean for about 50 meters, which is very impressive for their size. They use the tissues between their arms, called skirt, and their fins located on their head, the mantle, as wings for their flight. On the other hand, squids use jet propulsion to accelerate themselves to a very impressive speed, about 11 meters per second, which is significantly faster than Usain Bolt. So then I thought, although this is a high speed, they won't be able to stay in the air for so long if their motion is simply projectile motion. And that's why I want to investigate how things are able to fly and ultimately how lift works. I did some research on lift, and I came across this awesome definition from NASA. Lift is a mechanical aerodynamic force produced by the motion of the airplane through the air. Because lift is a force, it is a vector quantity, having both a magnitude and a direction associated with it. Lift acts through the center of pressure of the object and is directed perpendicular to the flow direction. So lift is a force, therefore it must be possible to express on a free body diagram. Here it is. It says here, lift is a mechanical force generated by a solid object moving through a fluid. Essentially, it means that lift cannot happen if the object is not moving through a fluid. About fluids are anything that does not have a fixed structure. For example, liquids and gases. Water is obviously a fluid, and air is a fluid too. As I've said, lift does not exist when the object is not moving through a fluid. That's why there's no lift in space, because vacuum is not a fluid. Today we'll be staying on Earth, so the absence of fluid won't be a problem for us. Obviously, the best example to demonstrate lift would be planes or birds, but I'm using squids because the Pacific flying squid is the starting point and inspiration for this project. So, this is my research question. How do squids fly and how we can learn from them to improve our aircraft? Well, we've sort of already answered this in the little intro I just did, so we've got to change it a little bit to fit more stuff into this video. To gain a deeper understanding of the concept and the connection between squids and lift, today we are going to investigate what lift is in its nature and how it is generated. There's actually some complex science in it. I won't be able to explain everything in 10 minutes, so I'll just skim through some of the concepts. Before I did my research today, I never learned anything formal on lift, and I remember being taught this theory about lift generation. It was a very long time ago and my memory was blurry, so I had to do some additional research to refresh that memory. Basically, this theory states that lift is generated by the difference of air pressure above and below the wings. According to a certain equation called the Bernoulli's principle, pressure is lower when a fluid is flowing faster. This theory is based on the assumption that the separated strands of air arrive at the end of the wings at the same time, and then since the air at the top half had traveled more distance, it has traveled at greater speed, and it is this greater speed that created the pressure difference. Since there's more pressure at the bottom, it lifts the wing upwards. I will be proving this theory of how lift is generated with a homemade model. Honestly, this thing I'm making is more of an experiment than a model. I used this styrofoam to sculpt various wing shapes, and by putting them on a sliding structure, they're able to move when there's airflow. So I have here 3 wing types. Number 1 is a flat wing. It should not be able to generate lift. Number 2 is the standard shape of a plane wing. It should be able to generate some lift. Number 3 is an irregular shaped wing, and the length of the upper half is increased to a certain extent. It should be able to generate the most lift. So, my reasoning behind this setup is that if the generation of lift is determined by the difference in length in the top edge and the low edge, then wing number 3 should be able to generate the most lift. This is followed by wing number 2, and then in last place, wing number 1. Let's see the videos of these wings in action and find out what actually happens. Note here that the setup is horizontal. I did this because any lift that was generated probably won't be strong enough to overcome gravity and actually lift the wings. This is wing number 1, and as we can see, the wing does not move a lot. This is expected because according to our assumption, lift does not generate. Let's watch this again. This is wing number 2, and it is able to move. This is also expected because in our assumption lift is generated by the difference in air pressure above and below the wing. Let's watch this again. Now this is wing 3, and as we can see, it doesn't really move. This does not fit our expectation, because since there is a larger difference in the distance air needs to travel above and below the wing, this should generate more lift. Okay, so the results weren't as expected. Wing number 3 did not generate lift. And why is that? Well, in fact, I always knew that the explanation of the air pressure difference had some holes in it. After carefully reviewing this theory, I came to the conclusion that this theory is false. Although I'm not saying that Bernoulli's principle is wrong, Bernoulli's principle is absolutely correct. Where it went wrong is that assumption we made, where we assumed that the air strands arrive at the end of the wings at the same time. There is no proof that this is always true, so this debunks the theory. In a simulation from Cambridge University, it was shown that air strands do not meet at the end of the wing at the same time. In fact, the top air moves way faster than the bottom air, and by the time bottom air reaches the end, top air has gone a long way ahead already. But wouldn't this make the false theory make more sense? Yes and no. While the difference in the air pressure does play a role in the generation of lift, the other factor that generates lift is more significant, and since air strands do not meet at the same time, the assumption is false by itself. So what is this other significant factor? Well, it works like this. Air is all around us, and each air particle interferes with its neighbors at all times. When a particle moves, its adjacent particles move as well. Applying this idea, air currents work the same way. If a current changes direction, the other currents nearby changes the direction as well. See here that wing number 2 has a curved bottom half. This means that the air will be deflected downwards when it hits the wing. So the nearby particles will be deflected as well, because they're pressured by the particles that did get deflected. Another idea I'm introducing is the Coanda effect. You know when you drip some liquid along a curved surface and it kind of sticks to that curve? That's the Coanda effect. It works the same way with air. When air currents hit the top half of the wing, it sticks to the curve and eventually it takes off at the end of the wing, where it heads downwards. So, overall the air currents get deflected downwards, and it's the air current that goes downward that generates the force of lift. Now that we've covered why the air pressure theory doesn't work and why the deflection theory works, what's the next step? I say now we can understand this free body diagram I showed before. You might wonder, since we know the law of conservation of energy, where did the lift come from? If there is no lift, then the aircraft is still going to do projectile motion. Well, airplanes generate lift by compromising their forward force, which results in an increase in drag, a backwards force. Because air particles are supposed to be deflected by the wings, they collide with the wings and apply a force onto it. Kinetic energy turns into thermal and sound energy via friction. And because a force is applied against the wing's direction of travel, its forward force is sort of reduced. That's basically drag. In conclusion, our hypothesis was wrong. Lift was not generated by the difference in air pressure above and below the wings. And the following factors contribute to the generation of lift: the deflection of air and the Coanda effect. So let's go back to where we started and see what we can find out now. We started with these squids that can fly, and now we know that they can fly because their pseudo wings could generate enough lift to slow down their descent. Although there's no solid evidence, we can infer that the cross-section of their wings are shaped something like wing number 2. Take a look at this picture. We can see the arm in the front, followed by the skirt in a relatively smooth curve. While squids aren't exactly experts at flight, they're marine animals after all. So I'd say that if we want to learn something from squids, it's gotta be their streamlined shape and jet propulsion technique. In terms of wings, we can learn much more from birds than squids. However, nature is still our best teacher. I'm sure we are all aware that many things we see in life are inspired by stuff in nature. For example, the B-2 stealth bomber's shape resembles the shape of a flying hawk. The shape of helicopters are derived from dragonflies. Velcro was inspired by the thistle plant, and so much more. So although we can't learn from squids in terms of flight, we can definitely learn more about how they propel themselves and how their body shapes help them move faster. I think if squids wanted to, they could definitely soar high up into the sky since they can go at such high speed. But considering their praise of various seabirds, they probably don't want to do that now. Although who knows what'll come out of evolution in several million years. Maybe they'll become predators of the sky, or even walk on land and shoot ink at each other just for fun. That's all for today. Thank you for watching.